So this is chapter 8 lecture. Now I'm going to focus on ionic bonds since I just finished up with covalent bonds. So you could put ionic bonds on top of this section of the notes. So ionic bonds are driven by a force called Coulomb's law, and Coulomb's law is going to be a major topic throughout this year. So the sooner you could incorporate that, the better it's going to be. So if you've had your physics, some of you have, some of you haven't, this is your Coulomb's law from physics. But realize that this is in the macro world. So this is large objects that we're talking about that follow Coulomb's law in this sense of the charge, you have distance, and you have K, and you have a force. In what we call the quantum world, so this is the quantum scale, so the small scale, we are now looking at a different way of interpreting Coulomb's law, or a kind of a way to think about it. So there's many different parts of this. You can have two, Q is always going to be charge. So you could have two positives, two negatives. We're just going to focus on one, which is positive and negative. So we are thinking of, again, making a bond in ionic compound. So there is a transfer of electrons from the metal to the non-metal, so you have a cation and an anion. So we want to know what's the force that keeps them together. So I think your book writes it more like this in terms of D is distance on the bottom. This I found from some other source. So R is kind of similar to the R you see up here, but not the same. So what we're looking at is energy. So this is the potential energy within the bond itself. So the energy, the interaction between the pair of ions, and it has a unit of joule. K is going to be a constant. And again, we're not going to do the math. We're going to do more of just the theory behind it. Q1 and Q2 are the ion charges. So again, I have calcium, let's say, is a +2, and chlorine is a -1. So that would mean that's a +2 and a -1 charge. So it comes from the ion itself. And then R, again, we could write that as D, lowercase d here. Is the distance between the ions in nanometers. Again, sometimes they do it in meters. It just depends upon the source that you use it. And again, we are not going to focus on essentially the math part of this, more of the concept. So again, you're going to have a relationship between the energy that is stored in that bond versus the charges of those ions versus the distance. So that's going to be what we look at. So we have something, so we break it down more according to the bond itself. So we are talking Coulomb's law is the potential energy in the bond, potential energy in the bond. So potential energy between two ions, the relationship is going to be, the potential energy is directly proportional to the product of their charges. So again, it's going to be Q times Q. So that's going to be the product of their charges, okay? So that's a direct relationship, while there's an inverse relationship between distance, okay? And again, please note, if you did not notice, when you did Coulomb's law in physics, R was squared, or the distance was squared. Here, the distance is not going to be squared. So we are just talking about the distance between them. So the Coulomb attraction, please understand that something that has a +2 ion is going to have a much stronger force than a +1 ion. So the higher charged ions will always have a stronger attraction. Okay, so that's according to charge. So that's going to be according to Q when we are discussing this. And then inversely proportional distance, the smaller ions will have a stronger attraction. So this is the distance we're talking about between those ions. So the smaller the ions are going to be, the closer they're going to get together. So how I'm going to ask this kind of question is going to be, again, using a periodic table. Okay, so you always have a periodic table. I'm going to give you a series of compounds. So I have sodium fluoride, cesium or cesium iodide, and calcium oxide. And I'm going to ask you to rank essentially their ionic bond, okay? So in terms of strong force. So if I look at sodium fluoride, that's a +1, -1. Cesium is +1, -1, but calcium is +2, -2. So really, when I'm looking at comparing these, I know that calcium oxide is going to be the strongest out of all of these. And then if I don't have a difference between their charges, I have to look at size. So I have to look at where they are on the periodic table. So I could see that sodium is up here, where cesium or cesium is down here. So sodium is smaller. And then if I look here, I have fluoride is up here, and then iodine is there. So these two are much larger versus these two, which are smaller. So the smaller ones are going to be able to get closer together. So you're going to have a shorter distance. So that's going to mean there is more stored energy, a stronger force that keeps them together. The other way I could ask the question is, again, because of size, it does depend upon who's attached to who. So if I mix this up and I did sodium iodide versus cesium fluoride, you would actually have to look up some numbers and do some calculations to figure out who has a stronger force. So instead, if I complete that one, I might give you the same anion attached to 3 different cations and say, okay, rank those. Because again, since I'm not focusing on the math portion of Coulomb's law in this instance, and neither is the AP test, more so you're just trying to compare things. So again, who is the smallest out of this group? Okay, who is the smallest cation? So that's going to be lithium. Okay, rubidium is going to be the biggest, and then potassium is somewhere in between the two. So lithium chloride is going to be the strongest force, while rubidium chloride is going to be the least force, or the weakest. So this is going to be the weakest, and this is going to be the strongest.